All right, welcome to our deep dive into week 6 of your Java course. Look, I know this week can be a real beast with threads, streams, exceptions. It's a lot, but don't worry, we're going to break it all down piece by piece so you can walk into your exams feeling confident. Let's get started.
Okay, so here's the game plan. We're going to start with the absolute essentials, how to stop your code from crashing. Then, we'll get into the fun stuff, making your programs blazing fast with multi-threading. After that, we'll figure out how to keep those threads from causing total chaos. And finally, we'll teach your program how to talk to the outside world using I/O streams before we wrap it all up with a rapid-fire review of everything you have to know for the exam.
All right, first up, let's talk about that heart-sinking moment every single one of us has had. You hit run, and your beautiful program just dies. We're going to make sure that stops happening.
Yeah, that looks scary, right? Array index out of bounds exception. It's like your program is screaming at you in a language you don't understand. But really, it's just a runtime error, what Java calls an exception. And it's what stops our code cold.
So here's the secret. Great code isn't about never making mistakes. That's impossible. It's about building code that can take a punch and keep going. It's about anticipating that things will go wrong and handling them gracefully instead of just crashing and burning. And that, my friends, is what exception handling is all about.
So, how do we do it with this magic little structure? The try, catch, finally block. This is your absolute safety net, and you are guaranteed to see this on your exam. You put your risky code, the stuff that might break, inside the try block. If it breaks, the catch block swoops in and, well, catches the error. And the finally block, that's the cleanup crew. It runs no matter what, error or no error.
And you can get really specific here. You can have multiple catch blocks, like a set of specialized tools, each one designed to handle a very specific type of error, like an arithmetic exception or a null pointer exception. Or you can just have one big general catch-all block to handle anything else that comes up. You can even create and throw your own exceptions using the throw keyword.
Okay, our code is stable, it's robust. Now let's make it fast. And I mean really fast and responsive. It's time to talk about multi-threading.
So what is multi-threading? Well, think of it like this. Instead of your program doing one thing at a time, step by step, it's like hiring a whole team of people to work on a project simultaneously. Instead of one single path of execution, you have multiple threads running in parallel. This can dramatically, and I mean dramatically, improve the performance of your applications.
Now, this is a classic exam question, so listen up. There are two main ways to create a thread. You can either have your class extend the thread class directly, or you can have it implement the runnable interface. The second way, implementing runnable, is almost always the better choice. Why? Because it separates the task, the thing you want to do, from the runner, the thread itself. It's just a cleaner, more flexible design.
Okay, and this illustrates probably the biggest, most common mistake people make with threads. You have to call the start method to actually create a new thread. That's what tells the Java system, hey, spin up a new worker and have them run this code. If you call the run method directly, you're not doing any multi-threading at all. You're just calling a regular method on the same old thread. It completely defeats the purpose.
So having multiple threads is awesome, right? But it's not all sunshine and rainbows. Once you have multiple workers running around, they can start getting in each other's way. If we don't coordinate them properly, we can end up with total chaos. So here's the central problem of all this concurrent programming. What happens when two or more threads try to change the exact same piece of data at the exact same time? Well, what happens is something called a data race. The result becomes completely unpredictable. Imagine one thread is trying to add one to a variable, and another is trying to subtract one. You'd expect the result to be 0, right? But with a data race, you might get 1, you might get -1. You just don't know. The threads interfere with each other, and your results become unreliable.
So how do we fix this mess? Luckily, Java gives us one simple, incredibly powerful keyword to solve this entire problem. And that keyword is synchronized. Think of it like a lock, or maybe a bouncer at a club door for your code. When you mark a method or a block of code as synchronized, you're telling Java, hey, only one thread is allowed in here at a time. Everybody else has to wait their turn. This ensures that operations on shared data happen one after another, not all at once, which prevents those nasty data races. This is the absolute core concept of creating what we call thread-safe code.
It's also important to remember that threads go through a whole life cycle. They get created, that's the new state. Then when you call start, they become runnable, meaning they're ready to go.
They can be temporarily paused or made to wait, which is the blocked or waiting state. And finally, when their run method finishes, they enter the dead state. You can control these transitions with methods like sleep, join, and even by setting a thread's priority.
All right, so our program is fast, it's stable, it's coordinated, but right now it's just talking to itself. To be truly useful, it needs to interact with the outside world. Read from files, write to files, send data over a network. That's what Java I/O comes in.
In Java, pretty much all data moves in what are called streams. Just think of a stream as a pipeline for data, flowing from a source, like a file on your hard drive, to a destination, like your screen. Your program can tap into this pipeline to either read data coming from the source or write data out to the destination. And what's really important to get here is that Java I/O is fundamentally divided into two camps. You're either working with raw bytes, that's 8 bits of data, perfect for things like images or executable files, or you're working with characters, that's 16-bit Unicode, which is what you want for handling any kind of text file. Knowing which one to use is key.
And believe it or not, almost all the I/O classes in Java inherit from just these 4 abstract base classes. For bytes, you have instream for reading and outstream for writing. For characters, you have reader for reading and writer for writing. So when you're working with files, you'll be using subclasses you've probably seen, like file instream and file writer.
All right, deep breath, let's do a quick fire round. These are the absolute, must-know, will be on the exam points. Ready?
First up, exception handling. The big takeaway is the try-catch-finally block. It lets your program handle errors without crashing. And remember, the key thing about finally is that it always executes, which makes it perfect for cleanup tasks, like making sure a file gets closed no matter what.
Next, multi-threading. 4 key things to drill into your brain. 1. Use implements runnable instead of extends thread. It's just better design. 2. You always call start to get a new thread running, never run. 3. Use synchronize to protect your shared data from data races. And 4. The join method is your friend when you need one thread to wait for another one to finish its job. Get these 4 down, and you've got most of your assignment questions covered.
And there you have it. That's your Week 6 toolkit. You've learned how to make your code safe, fast, and connected to the outside world. But the real power comes when you start combining these ideas. So think about it. How could you use multiple threads to read and process a massive file super quickly? How would streams and threads work together? Keep exploring, keep building, and you'll do great.